Hi everyone, today I present GRAPE, which stands for Gaussian rendering for accelerated pixel enhancement. GRAPE is a super resolution method that can upscale to any target scale, but still runs fast and lightweight. It does this by predicting 2D Gaussian primitives and rendering the high resolution image efficiency. Most super resolution models are built around big scales, but in real product, zooming a photo, a video player, or an image viewer, people expect smooth continuous zoom. That's what arbitrary-scale super resolution is about, using one model to generate output at any target scale. The remaining question is, can we do that while staying fast and lightweight? ASSR method exists, but efficiency is the bottleneck. If you stick to scale-specific SR, you're locked into preset ratios, or you end up maintaining multiple models. If you use implicit representation, you usually query a network at many coordinates, which means the computation grows with the number of output pixels, so high-resolution output can get slow. Here's the core idea of GRAPE. Most SR methods ultimately try to predict pixels. GRAPE believes that it predicts a compact set of 2D Gaussian primitives and then renders the final image. Concretely, it passes the LR image through an encoder and forms a latent grid that corresponds to 4 times as many positions. So we get n equals 4 small hw Gaussian splat. Then a single layer has predicts just 8 numbers per splat. The RGB color, a rotation angle, 2 scale values for anisotropy, and a 2D offset. Once it has those parameters, a differentiable 2D rasterizer does the heavy lifting, splatting Gaussians onto the output canvas, so it can generate super resolved image at any scale efficiently. Here's why GRAPE runs best. It avoids a heavy decoder and instead predicts Gaussian parameters using a tiny pointwise head. After that, it relies on a GPU-friendly 2D rasterizer to render the output at the target resolution. For a 1080 output, the total time is 40.9 milliseconds, and roughly 85% of that is in the encoder. That means the rendering step is relatively lightweight, and the overall pipeline stays efficient even when the output gets large. This figure highlights efficiency at 4 scales on urban 100 dataset. GRAPE runs at 60.433 fps while using 1.10 GB of GPU memory. In the same setting, LII app reaches 3.06 fps with 8.26 GB. Gaussian SR reaches 6.19 fps but uses 16.15 GB, and GSA-SR runs at 0.2 fps with 7.89 GB. Next are the quantitative tables across datasets and scales. Table 1 reports speed up on urban 100 over a wide range of integer scaling patterns, with PSNR shown in parentheses. Table 2 and 3 show a consistent pattern on Z5, Z14, BSD 100, and div2k. GRAPE maintains competitive PSNR while delivering much higher throughput. Here are qualitative comparisons at 4 scales focusing on challenging urban 100 scenes. These examples are dominated by repeated structures, window grid, brick patterns, and thin edges, where super resolution methods often introduce smearing or distorted geometry. In the zoom crops, GRAPE tends to keep lines straighter and patterns more regular, especially around grids and repeated textures. Compared to simple upscaling, the results show sharper boundaries and clearer repetition, which makes the overall image look more stable when zooming in to fine detail. To wrap up, GRAPE treats arbitrary-scale super-resolution as a rendering problem rather than relying on a heavy pixel decoder. By predicting 2D anisotropic Gaussian primitives and reconstructing images through efficient rasterization, it keeps the model compact while achieving a strong speed memory trade-off and competitive image quality. This makes GRAPE particularly suitable for efficiency-critical scenarios such as interactive zoom and resource-limited deployment. Thank you.